Hello again. Here is review sheet number 2, the second review sheet from the fall, as we are now getting ready for the final exam. Remember, you could scrub forward and find the question you want. And also remember, my apologies if it's not particularly smooth. I'm just going to run through this. And so if I'm not particularly eloquent or if I make a flub with my explanation, I'm just going to correct it, but keep going. All right, let's start with kind of easy ones, I hope. Which one of these is not a vector? I talked about this in the last review sheet. A vector is a quantity, a property that has a spatial direction associated with it. Like you could say it's going to the east or going north. So velocity is a vector. So the question asked which of these is not a vector. It doesn't matter what kind of velocity, change, average, initial, those are all vectors. Acceleration, even though I really haven't brought that up in this second unit here yet, is a vector as well. You could be accelerating to the left, you could be accelerating down, lots of accelerations. Speed is a vector, so we'll circle that one. You just say you're going 50 miles per hour. You don't specify the direction, therefore you're talking about the speed. And position is a vector as well. Circle the one vector units below. So it helps if you remember the formula. I bet you already know or remember it, even though it's been a long time. That velocity, remember, is your change in position, like how far you go, divided by the time. So any velocity unit is going to be some kind of distance unit, like let's say meters, divided by any kind of time unit, like seconds. Or it could be kilometers per hour. Hey, there it is right there. So there is the velocity unit. Now acceleration, again, we haven't got to this yet in this review sheet. The formula for acceleration is delta V over t, the change in velocity over time. So that's going to be some kind of velocity unit, like meters per second, divided by some kind of time unit, like seconds. Or let's do another velocity unit. Let's do, for example, centimeters per minute, divided by hour. So that's another acceleration unit. So let's take a look for acceleration units like that. Well, here's one right here. Centimeters per second per minute. That's a velocity unit divided by a time unit. It's telling you how many centimeters per second your speed is changing per minute. Or this one right here. Now, this is kind of tricky. It might look kind of funny, but let me go back to this one right here. It's not going to be quite the same answer. But if I took centimeters per minute and rewrote it like this, now I'm supposed to take centimeters per minute and divide by an hour. So that's the same thing as multiplying by 1 over an hour, right? And then what do you get? Centimeters per minute hours. So another way you might see an acceleration unit is a distance unit divided by 2 time units that are multiplied by each other. So that's what that one is showing you right there. It's a distance over a time times a time. So you could almost pronounce that one meters per second per hour or meters per hour per second. And although we don't have any others on that list, remember that if we, for example, we take, not that one, where's that right there? Meters per second, you could rewrite that as meters per second squared. So that's another way you'll see an acceleration unit is a distance over a time squared. Okay, not a big deal. I don't have a lot of room to ask a lot of these questions on the final, so it's not likely I'm going to ask one of these questions, but you should know it. All right, let's go to position graphs. So I told you in the last review sheets, you better pay attention to whether it's a position graph or a velocity graph. We only did position graphs in that first unit on review sheet 1, but then when we got to the second unit, I introduced velocity graphs. So pay attention because they're going to have different answers. Now I know I reviewed this in the first review sheet, but again, go ahead and skip forward if you don't want to hear this. But let's just review some of the things about position graphs. So we have position, a little bit crooked there, versus time. And I'm going to call this up and down. But of course, that's the positive and that's the negative direction. So just really quickly, I'm not going to spend a lot of time on this. I'll use green here. See if you can answer these questions as I draw them. What does this mean? It's supposed to be parallel to the x-axis. You're stopped, right? Your position is not changing. So a horizontal line means you're stopped. This means you are moving, but if it's a straight line like that, not horizontal, but straight, that means it's a constant velocity. Now, which direction are you heading with that green line? Towards the positive. What about this? That's a constant velocity, but which direction are you heading? Towards the positive or towards the up. You're heading up because we're in the down area, whatever we're calling down, but we're heading towards the up. What does this mean? It means you're slowing down because remember, the shallower the slope, the slower you're going. Steep means, I didn't say that one, but steep means fast. Shallow means slow. So we're going from being kind of fast, where it's kind of steep there, and then as we slow down. Here is speeding up. If we do something, oops, I didn't mean to do that. If we do this, it's not very smooth, but we're getting steeper. And then one other thing that's kind of tricky, maybe I'll go ahead and change colors here, is what if we do this, and then we do this? What's happening right there? Well, you were heading in the down direction, right? We're not down yet, but we're heading towards the down. And now we're suddenly heading up. So when you have that change of direction on a position graph, that means you are literally changing direction. You are going in the opposite direction. Okay, so there's just our little review, just in case you needed it. But let me get rid of that because we might need that space later. So let's actually deal with the question now. So it says, which way is it heading from 2 to 4 seconds? So this part right here. Well, we're in the west initially, but we're heading east. So we are heading east there. It wasn't until 4 seconds that we got, quote unquote, into the east, but we were always heading to the east. Or you can say we're heading to the positive direction. During what times is it stopped? So remember, stopped on a position graph means horizontal. Write these down on your note sheet for the final if you want to. Just say position graph and then put all the things that are true if you don't think you can get it, just looking at it live, because I know you're under a time stress during the final. So it's going to be 0 to 2 seconds. At what time did it turn around? So I just explained that whenever the graph changes direction on a position graph, you are changing directions. So that's going to be 9 seconds. When did the object suddenly slow down? So remember, on a position graph, the steepness tells how fast you're going. So right here, we go at a certain speed, which is related to its slope. But then notice at 5 seconds, our slope suddenly becomes smaller. So we've slowed down right at 5 seconds. We didn't slow down here at 9 seconds. We actually changed directions and sped up. So just at 5 seconds did we slow down. Okay, actually I did similar to this one as a bonus question, letter E, on the last review sheets, but let's do it again because it's important enough. It's something that we tend to ask on test. Try to get the velocity from a position versus time graph. So remember this, write this down. Don't miss this because it's, I would say it's likely to be on the final. The slope of a position versus time graph gives you the velocity. So we want to know the velocity at 7 seconds. Well, what is the slope of the line during that time? Well, notice for that entire time from 5 to 9 seconds, we have a constant slope, a constant velocity. So I just want to know the slope of that line, and that is the velocity. So be careful of what's written there. Don't think that the rise is 2 because it's 2 boxes higher. I'm going by 2s. So my rise is 4 meters. And what's the run? From 5 to 9 seconds, that's 4 seconds. So the slope is 4 meters over 4 seconds, or 1 meter per second. So that is the velocity. And you could say positive if you want to, or you could say 1 meter second to the east. What is the displacement, or delta x, or change in position, for the entire 10-second trip? Let me kind of maybe erase this so it is not so messy here. Okay, so what is first of all, the displacement? Oh yeah, that's pretty easy to see. We haven't got to G yet. So we started right here at -4, and we ended at +2 after 10 seconds. So we started at -4 and we ended at +2. So how much did our position change by if we went from -4 to +2? it changed by positive 6 meters, or you could say 6 meters to the east, whichever one you want. So what is the average velocity? So remember, the average velocity, you'll have written all these equations down, is the displacement over the time. So that's going to be positive 6 meters, but you can leave out the positive, over the 10 seconds that it took, or 0.6 meters per second, or 0.6 meters per second to the east. Okay, that was a good little review there. So let's go to number 4, and now we have velocity graphs. So again, I'm going to take a little time here to do a little mini lesson. So let's go back down here and find a blank space. So now I'm going to draw a velocity graph, and we'll do a bunch of options. And remember, there are a lot of questions in the homework, and also remember that in one of the slideshows, I did a lot of examples, and I think you guys got really good at these. It's just that they're confusing after you do position graphs because the lines and the curves all mean different things. So let me just draw some and see if you can figure out what these lines represent. So let me try a green one here. What does this mean? Where again, I meant it to be parallel to the x-axis. Now on a position graph, this would mean that you are stopped. But this is not stopped because we're graphing velocity. For example, this might be in meters per second. So this might be some value like 4. So that means you're moving at 4 meters per second. It's actually giving you velocity. So that's not stopped on a velocity graph. That is actually moving, but you're moving at a constant velocity. So again, write this down on your note sheets. If you think you'll have trouble with it, write down velocity graphs, underline it, and then put some facts about it. If you have a horizontal line, it means you're moving at a constant velocity. It doesn't necessarily mean zero velocity. How would I draw something that does mean you are not moving, you have zero velocity? Well, it would have to be specifically, get my green again, right on the x-axis. That means you have a constant velocity, but a constant velocity of 0. So stopped on a velocity graph is only when the graph, the line, is touching the 0, the x-axis. Actually, I'm going to give some directions here. Like before, I'm going to call this up and down. It could be east and west or whatever. But remember, these are always positive. These are always negative. All right, let's draw some more. Let's try some orange one. What does, actually, I'll go back to the green one that I just drew. I'll just ask you about that one. Which direction are you heading if that's your graph? Up, right? Because that is up. But let's try another one. I'm going to try this in orange. First of all, let's deal with which direction are you heading. Now, if this were a position graph, what would you say? You would say you're heading down or in the negative direction, because although we're not there yet, we're heading that direction. This is not a position graph. This is a velocity graph, which is actually giving you the velocity. So what is the sign of the velocity the entire time for that orange line segment? It is up. You are heading up the entire time. So for velocity graphs, which way you're heading is just which side of the graph that you're on. So if you're on the top half of the graph, you're heading in the positive direction. If you're on the bottom half of the graph, you're heading in the negative direction. Okay? I know it's kind of complicated, but you'll get good at these again if you just practice. But what's happening to the velocity for that orange one? Well, we're starting up here at maybe that's 5 meters per second or something, and we're ending up down here where it might be 1 meter per second. So that means you're slowing down. That means when you have a slope that's not horizontal on a velocity graph, you're either speeding up or slowing down. Okay, let's try another one. I think it's going to come back to you. For this one, first of all, which direction are we heading? Down the whole time. We never got up here, so we never started moving up, so we're moving down. But what's happening to the speed as time progresses? Where we're going from a pretty high speed, this might be -4 or something, to a pretty low speed. So we're slowing down. So a thing you could write down is whenever your curve or line is getting closer to the x-axis, you're slowing down. So maybe to do a counterexample, let's do magenta. What are we doing there? we're speeding up. We're getting farther from the x-axis. So write that down. Getting closer to the x-axis, slowing down, on a velocity graph that is. Getting farther from the x-axis, you're speeding up. Now some other things that are kind of interesting is let's do, another color, doesn't matter. We'll do like a dark green. What if we did this and we cross the x-axis? What is the significance of that point there? Well, actually, let's think of the whole graph and we'll understand what's going on. So we start down here, we're changing velocity, we're slowing down, right? Slower, 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 slower. And what's our velocity right there? 0. But which direction was I heading this entire time, even though I was slowing down? I was heading down. So from here to here, you're slowing down as you're moving down. I know it might not make sense as far as what physically is happening, but then after I pass it, which direction am I heading? Now I'm heading up, and I'm speeding up as I'm getting farther from the x-axis. So now we're going up. So what's the significance of passing the x-axis in a velocity graph is you're changing direction. Remember that for a position graph, the way you change direction is you change the slope from one way to the other. But here, the way you indicate change in direction is when you cross the x-axis and are now going in the opposite direction. Okay, I don't want to spend much more time on that, but that's kind of the idea. Now, a couple other things. One is, let me just do a couple more, then we'll move on. I'll just use the same color. We'll use magenta. What if we did this? I'll overwrite that one. And we didn't, oops, I meant to do that. So let's interpret what's going on. Which direction are we heading from here to here? We're heading down, right? Because we have a down velocity, but we're slowing down. So I shouldn't have used down because now I have to say we're slowing down as we're going down. But then when I get to here and I move this way, am I changing direction? No, I'm still heading in the down direction. So I'm going down the whole time, but here I'm slowing down. And then suddenly I'm speeding up, but I'm heading down the entire time. Sorry about my handwriting. So these are tricky. And then the final one I'll mention is, I don't do these a lot, but what if I have a curve that kind of does this? Well, maybe backing up a bit, again, I'm not going to record this, is remember I said the velocity is the slope of a position graph, or saying it backwards. If you take the slope of a position graph, it gives you the velocity. Well, if you take the slope of a velocity graph, it gives you the acceleration. So when you have a curve on a velocity graph, that means your velocity is changing, because remember your velocity is changing because we're getting faster here as we're going farther away from the x-axis. But our acceleration is also changing because the slope is changing. We're starting with a pretty big slope here. That means you have a high acceleration. But notice that the slope is getting smaller and then smaller. So the acceleration is simply the slope of a velocity graph. And so if you have a curve where the slope is changing, that means your acceleration is changing. And remember, we had a term for that. You remember that? Jerk. Jerk is the rate of change of your acceleration. Okay, way too much on that. I'm sorry that you had to sit through that, but maybe it was useful for some of you. Okay, let's go back to the question now. We'll hopefully go quicker. So here we are with a velocity graph. Again, pay attention whether it's position or velocity. Which way is it heading from 5 to 9 seconds? So this part right here. Well, don't get fooled. Don't say, oh, we're heading towards the west. No, this is an eastern velocity the entire time. So we're heading east. During which time is the acceleration the greatest? So as I just said, the slope of a velocity graph gives you the acceleration. So what it's actually asking you, kind of in a code there, is where is this slope the greatest? Well, isn't that from 0 to 2 seconds? Yeah, didn't mean to do that. All right. When did it turn around? Remember, I'm not going to re-explain this too much, but right there at 1 second. Because from here to here, we're heading to the west, right? But slowing down. But once we're here, we're heading to the east. So we changed directions when we crossed the x-axis. Again, write that down. Is it stopped from 2 to 5 seconds? Now, you might say yes, because, oh, look, it's horizontal. No, that's only for a position graph. So as long as you're not on the x-axis, a horizontal line on a velocity graph means you are moving, but moving at a constant velocity. So we are not stopped. We're moving at 20 meters per second. What is the velocity at 7 seconds? So here, we want to know the velocity at 7 seconds. Now you might say, hey, let's take the slope. Nope. You find the slope of a position graph to find the velocity. If you took the slope of that line right here, that's going to give you the acceleration, which we're about to do at a different time in part F. The velocity is what we're actually plotting here. So if we want to know the velocity at 7 seconds, all we have to do is read across and see what the velocity is. And so the velocity is about 15 meters per second, or you could say 15 meters per second to the east. So now let's do the thing with the slope. What is the acceleration at 1 second? So right here. Now a trick could be a good multiple choice question, is I'll give you as a choice that the acceleration is 0, because you look at 1 second and you go, oh, it's 0. No, that's the velocity. Remember, or write it down, the acceleration from a velocity graph is the slope. So we want to know the slope of that line because the slope is constant. Not this line, but this dark one right there. So what's the rise? And again, it's not 4. The rise is 40 meters per second. That's the units of the y-axis. And what's the run? The run is 2 seconds. So the acceleration is 20 meters per second, or of course you can write that as 20 meters per second squared. And it's positive. So the slope will always be positive. I should say the acceleration is always positive if your slope is positive. What's the slope of that? That's negative, so the acceleration is negative. All right. Hopefully I'll go a little faster, but I just want to make sure I explain things fairly well so you remember some of the stuff from long ago. Number 5, a car starts at 10 meters per second east and ends up going 50 meters per second west. What is the change in velocity? That's the delta, remember. Now let's do this logically, and then plus I'm going to use my little speedometer or velocimeter technique that I think worked for some people, but you eventually didn't need it anymore. So one way we can do that is just think about it logically. We're heading 10 meters per second east. That's our velocity. And then we later are going 50 meters per second west. So what's the change in velocity? Well, to get to 50 meters per second west, I have to lose all that speed, the 10 meters per second east. So I'm going to have to change my velocity by 10 meters per second to the west. Plus, I need to add 60 more meters per second more to the west. So that's going to be 60 meters per second to the west. Now, what I was talking about with my little velocity thing here is, let's say this is east and this is west and this is 0. It's like my little speedometer thing here on is that the term? I just said speedometer, it didn't sound right. But anyways, we're starting at 10 meters per second east. So I'll write 10 here. And where did we end up? 50 west. So your change is, remember, sorry about the sloppiness of that drawing, is from there to there. It's from where you start to where you end. So notice I had to change by 60 towards the west. Now, one final way you can do this is, I think I have this in the answer key, is the delta V equals the final minus the initial. The change in anything is always just the final value minus the initial value. Now, what I might do for this, because it's weird to subtract cardinal directions, east and west, is let's pick a direction to be positive. I'm going to say west is positive. So this is going to be positive 50 meters per second, right? And this will be negative 10 meters per second. So if you do that, you'll say my final velocity is positive 50 meters per second, and I'm subtracting the initial, which is negative 10 meters per second, which gives us positive 60 meters per second, which is to the west because I defined west as being positive. So that's, again, what most physicists will do. They'll just change cardinal directions to positives and negatives and just add and subtract, because that would be weird to say 50 meters per second west minus 10 meters per second east. What does it mean to subtract east from west? But typically, if the numbers are convenient, you could just do it in your head with east and west. Okay, let's get to V average. Now, one thing I'll repeat many times on this is whenever I give you an initial velocity and a final velocity, you could always find two things from that. The delta V, the change in velocity, and the average velocity. So remember, that's always in your arsenal. Given an initial and final velocity, you can find both. So let's do it back with, which is already defined west as positive, just doing that. Your average velocity, one way to write that, is V initial plus V final over 2. It's literally just the average. So I'm going to take my initial, which is negative 10 meters per second, and add to it my final, which is positive 50 meters per second, and divide by 2. And so that gives me 40 meters per second in the numerator, but I'm dividing by 2, so I get 20 meters per second, which is to the west because I'm using the convention that west is positive. Now, what if you just wanted to use east and west and not do that? I'll erase this to get out of the way. I could do the same equation, but I can say my initial velocity is 10 meters per second east, and my final velocity is 50 meters per second west, but I'm going to divide by 2. Don't forget to do that. So what do you think you get when you do 10 east and 50 west? Because they're opposite directions, you just have this, inclination to subtract those. So yeah, it's going to be 40 meters per second in the numerator, but 40 meters per second which way? Well, in the way that's bigger, the west. So that's going to be 40 meters per second west divided by 2, or 20 meters per second west. So again, sorry, that took way too long to explain, but I know you haven't done this in about, 5 or 6 months, so maybe you just need a little bit of reminder. Yeah, I know I erased it, but you have the answer keys as well. Okay, let's try this one. The initial velocity is negative 24 meters per second, and it has a change in velocity of positive 17 meters per second. What is the final? And remember, always the final whatever is just the initial whatever plus how much it changes by. Yes, write down that equation, but it's kind of common sense. To get the final value, you just take the initial value and add to it how much it changed by. So conveniently, it already gave me positives and negatives. So I take my initial of negative 24 meters per second, and I'm adding how much it changed by, which is positive 17 meters per second. So I get negative 7 meters per second. Not too hard. Again, on their own's not too interesting, but we're about to get to some questions where that'll be part of a bigger question. So make sure you have those skills of quickly being able to find delta V and V average, or a V final from a V initial and a delta V. Those will be all kind of needed in our toolbox to solve more complicated calculation questions. So just get good at them. Again, you don't have to show your work on the final, but just make sure you're efficient at solving them. Okay, let's do some more graph questions. There probably will be quite a few graph questions because they lend themselves to quick multiple choice questions on the final. So you won't get one like number 7 because it's going to be multiple choice. I could draw something and say, does this look like it's what I'm saying? But you won't have to draw it yourself. But let's go ahead and do this. Draw a position graph. So again, remember, always pay attention what kind of graph it is. For an object that starts at the dot and is heading south pretty fast, passes the origin, but is gradually slowing down to a stop. So we're starting here. Now, how do we draw heading south? We have to be heading down towards the bottom, right? But it's starting pretty fast. Remember, on a position graph, the slope is how fast you're going. The steeper the slope, the faster. And it says it's gradually slowing down. So our slope needs to gradually slow. So it passes the origin. So I got to go past the origin here. So I'm going to draw something like that. And gradually slowing down to a stop, which means it's horizontal. That looks pretty good. Yours might not be exactly the same, but that kind of is accomplishing it. Well, it is accomplishing it. We were going south, going pretty fast at first. It was steep, but we slowed down. It was becoming less steep, and we became horizontal. So that is stopped. All right, here's some interesting ones. Again, you won't have to draw, but you should understand how these work. The top are some position graphs, and we're going to draw a velocity graph that represents that motion. So let's interpret what's going on, and then we'll draw it. So here we're starting, I won't write it all down, I'll just say it verbally. We're starting in a negative position. That's actually not going to be too important for the bottom. But we're heading which way? We're heading in the positive direction. And then we cross the origin and we're still heading in the positive direction. So we're heading the positive direction the entire time. And what is our velocity like? Is it changing? No. Remember that on a position graph, if you have a constant slope, your velocity is constant. So in other words, all that's saying, that graph, is that we're heading in the positive direction at a constant velocity. Well, how do we write that on a velocity graph? Just like this. We're heading in the positive direction at a constant velocity. Remember that a horizontal line on a velocity graph does not mean that you're stopped unless that horizontal line is on your x-axis. So that's the answer to that one. Okay, the second one's a little bit trickier. So for this initial portion from here to here, we're heading in the negative direction, right? That's the position graph, at some constant speed, and that looks pretty fast, right? But then at that time, we start heading in the positive direction. Sure, we're not in the positive region yet, but we're heading in the positive direction at a constant velocity. But importantly, how does the velocity compare for this portion compared to that initial portion? It's slower, right? So we want to draw something on a velocity graph that represents a constant velocity going in the negative direction. And then at this time right here, which represents about right there, we need to start going in the positive direction at a slower speed. Okay, so first let's tackle negative direction, constant speed, pretty fast. Maybe this, right? That's a constant velocity because it's horizontal. It's the negative direction, and that's pretty fast. We're far away from the zero. But then suddenly, over here, we're going to be going positive direction, but slower. But it's a constant velocity because that position graph was a constant slope. But how do you connect them? Well, that looks almost like immediate acceleration, so it doesn't matter too much. I'll just go ahead and connect them like with a straight line, but that's almost well, it is impossible to have a vertical line. That would mean infinite acceleration, but I'm not really caring about that. So yeah, look at those two, and that's how the velocity graph represents that movement in the position graph. We're going fast in the negative direction at a constant velocity, then now we're going slower at a constant velocity in the positive direction. I hope this is fun. You're finding this useful. Number 9, on the right is a velocity graph. Draw its position graph. So the opposite way. It's a little bit more interesting here. So let's interpret the motion for the velocity. We're starting at zero velocity. We're stopped initially, but we're immediately moving. But are we traveling at a constant velocity here? No. This is a velocity graph. We're speeding up, right? We're getting farther from a zero velocity. So this is speeding up at with a constant acceleration, because remember the slope of a velocity graph is the acceleration. So since the slope is constant, our acceleration is constant. But we're heading in which direction the entire time? Negative direction. So I want to show on my position graph something where we're going in the negative direction and speeding up. Now, it doesn't matter where we start in the position graph, because nowhere in the velocity graph does it say where you're starting. 0 on the velocity graph is not saying you're starting at the origin. It's just saying you're starting with a 0 velocity. So I can start this wherever I want. So just to match the answer key, I'm just going to randomly start here. Now I need to go in the negative direction, so I need to head down, but I need to speed up, which means I need the slope to get steeper and steeper and steeper. So that is heading in the negative direction and speeding up. All right, let's keep going. There's a chance I do this in 2 parts because this is taking a while. We got still 2 more pages. Draw a velocity graph for this scenario. Again, you won't have to do this, but again, the knowledge might help you as we go over this. An object starting at 10 meters per second, so that's initial velocity, so right there, accelerates at 5 meters per second squared for 4 seconds. Blah, blah, blah. So let's deal with that. So we need to know on this velocity graph how the velocity is going to change. Well, again, I haven't brought this up yet, but you will memorize or write down that the change in velocity is the acceleration times the time. So using the given information, 5 meters per second squared times 4 seconds, the velocity is going to change by 20 meters per second in the positive direction. Now that took 4 seconds. So here's 4 seconds right there, right? But we're changing our velocity by positive 20. So if we started at positive 10 meters per second, after 4 seconds, we're going to be at 30 meters per second. So if we're assuming it's a constant acceleration, it's going to look like that. Then finishing the problem, it says that it stays at that new velocity for 2 seconds. So it stays at 30 meters per second for 2 seconds. Then it slows down to a stop over the next 3 seconds. So by the time we get to 9 seconds, it should be stopped, and we'll just assume it's slowing down steadily, a constant acceleration. Okay, that's it. Again, you won't have to draw them, but maybe that'll help you understand some things. All right, page 2. Now we're going to start doing some calculations. That might be the scary part for some of you. An airplane is flying at 500 kilometers per hour when it has an acceleration of negative 20 kilometers per hour per second for 4 seconds. What is its final velocity, VF? So again, I'll come down here. You might have seen this earlier. These are some equations we'll use, plus I'm going to introduce 1 or 2 others that we really didn't learn until a later unit. But for this final exam, you could use whatever equations you want. So we're going to end up using this equation, delta V equals AT, to do this problem. Now, how do I know that? Remember, I told you the way you have success is to identify what the given information is and find which equation works for you. So this sounds like a velocity, right? And I'm not saying it's changing. Actually, it is. I said it's initial velocity. Okay, sorry. It does say it's initial. It doesn't say that, but it's implied by the fact that I said what's the final velocity, because we are accelerating. So that must be the initial velocity. We're looking for the final velocity. We don't know that. We're given the acceleration, and we're given the time. So again, you don't have to do DESPA, of course, but I'll write them down to remember and say, what are we going to use? What equation we're going to solve? So we have V initial, A, and T, and we want to know V final. So look down here, and what you would do is on your note sheet, you'll go, well, which equation can I use for that? And hopefully you'll get this one. Now, what might help you also is if you think about delta V as V final minus V initial, you can always say V final, well, I'll just do it this way, V final minus V initial equals AT. And that might even look more familiar when you look at this, because look, we have V initial, A and T, and we're looking for V final. So that's pretty much what that one is. Okay, I really, okay, I didn't mean to confuse you. I kind of really screwed you up there. Get rid of that equals, because I know that's kind of bothering you. That should be minus. Okay. But we'll do it kind of the old-fashioned way. I didn't do that. I just used delta V equals AT. So given that we know A and T, again, even if you're not sure what you're doing, you just say to yourself, well, I have an A, I have a T, and there's an equation of delta V equals AT. Well, I'll just use it and see where that leads me. So let's do that, even if we don't, because that's not going to give us the answer yet. So the acceleration is, and if you don't mind, well, I'm going to go ahead and put units. I was going to say I'm not going to put the units, but just because I'm running out of space. But I'll do it. 4 seconds. So the seconds cancel. So our change in velocity is negative 80 kilometers per hour. Okay. Now we could do the rest of this in our head, but I can show you again how we can get V final. So if we're initially going positive 500, and we change by negative 80, and the units match kilometers per hour, what is the final velocity? 420 kilometers per hour. Okay, and that's my answer. Now I'll erase this in a second to create some space here. If you want, you're not doing DESPA, but if you're a little confused by that, remember that the V final is always your initial velocity plus your change. So your initial was 500. Again, I'll leave out the units this time. Plus your change is negative 80. And what's 500 plus negative 80? 420. All right. So again, the way you get success from this is by identifying what the given information is and just finding the equation that works. And like I said, one technique, I kind of mentioned this all during the fall, is if you don't know what you're doing, just look for an equation and start solving for something. You're going to almost accidentally stumble upon the answer if you just don't give up and just use the right equations. So we'll keep using that technique. 12, your car can accelerate at 6 meters per second squared. That's my A. How long, it's looking for T, would it take for it to go from the initial to V final. Okay, looking familiar? So we're given V initial, V final, A, and we're looking for T. Okay, so which equation do you think we're going to use? Because remember, whenever you have V initial and V final, that's going to be your delta V, right? So we're going to end up using delta V equals AT. Or just going ahead and solving for it, we're solving for T, right? It's going to be our delta V over A. Make sure that you don't do A over delta V, even if you have to write it down in your notes. So let's find the delta V. Remember, whenever you have initial and final velocities, you should be able to just quickly find what the delta V is. So what did the velocity change by if it went from 10 to 36? 26, right? I'm never going to write that down as work. So it changed by 26 meters per second, and then the acceleration was 6 meters per second squared. So sorry, I'm running out of space, but that's going to equal, what, 4 1/3, or scientists prefer decimals, even though it's not as exact. And then the meters per second will cancel meters per second, but then you're going to have a 1/seconds in the denominator. But when you flip it over, that's going to end up being seconds. And again, if you do equations right and you have your system of units that are consistent, like SI, you'll end up with your proper units. Okay, let's do a hard one. I mean, again, at the time, once we learned how to do a thing like 13, it ended up being easy for you. But now it might look kind of hard because we haven't practiced this in so long. So let's write down the given information again. And this time I'm just going to write it below. We have our initial velocity of 36 meters per second. We have our final velocity of 8 meters per second. It moves 88 meters. What property and what symbol is that referring to? That must be your displacement, delta x. What was the acceleration? So we're looking for A. So here's the way we did this, because the only equations I taught you at this point were those. Now I'm going to redo this problem after this using one of the equations we learned later, because you might even recognize there might be a little bit of a shortcut here. So here's the way we did this, and this was supposed to be a challenging question at this time, about a month and a half into the semester, is we're looking at this and thinking, okay, remember, I always tell you, whenever you're given the initial and final velocity, we also know the delta V and the V average. So that's what we can think of. So let's think what we have and what we're looking for. We're looking for A, right? But we're going to get A, so there's different strategies of how to think about that. If we know the delta V and the T, well, yeah, we can get the delta V. So we can get the A. If we have the delta V, we're going to get that. But we need to know the time. I'm not given the time. So you think to yourself, well, how do I get the time? Oh, there's another equation I know. Sorry, my brain's not working. Delta X equals V average T. Sorry about that. So you'd say, there we go. If I could get the time by using my displacement and the average velocity, then I can plug the time into this with the delta V I'm going to use and get the acceleration. You see that? I know it's difficult right now because it's been so long, but let's do that. And I'll erase this. I'm going to do it here. But one of the keys here is, like I said, you just need to remember that given the initial and final velocity, you can find two different types of velocities from that. So let's first find the average velocity. So remember, the average is the average, I won't write it down, between 36 and 8. They're both going the same direction. So the sum of those is 44, but you divide by 2. So the average velocity is 22 meters per second. Okay, so now we're going to use delta x equals V average T to solve for T. So T equals delta x over V average. So that's 88 meters. And again, I'm using nice convenient numbers, right? So that's going to give me 4 seconds. So by using the average velocity and our first equation that we learned, I found out it's going to take 4 seconds. Now I can use delta V equals AT, or I'm solving for A. But now I need to know the change in velocity. So notice we started at 36 and we ended at 8. So how much did it change by? Not 28, negative 28 meters per second. And the time it took was 4 seconds. So the answer is, what is that? Negative 7 meters per second squared. And there's our answer. Okay? So pay attention, because if if all these are multiple choice questions on the final, and I could have positive 7 there as choice A, and you might jump at that one. And then later on, like part E, it'll say negative 7. So make sure you get that. Now remember, it's negative 7. I'm going to redo this problem another way by mentioning a certain equation that you can use. Now remember, as I just said a while ago, oops, I don't want to erase all that. Let's just erase the stuff down here. That when we did this problem in Unit 2, these were the only equations you learned. But on the final exam, you could use any equation. So in Unit 3, we learned, actually derived it, another equation, and that was this. Delta x equals v initial t plus 1/2 at squared. Again, don't panic. It's not like I'm asking you to derive that anymore. That will be something you'll have written down on your note sheet for the final, and let's see if we can use that. I think that's the one I want to use. Actually, no, that's not the one I use. Okay, I had to look. There's another equation. So again, I'm not re-recording this. So you'll have this one written down as well, even though we didn't use this very often. V final squared equals v initial squared plus 2 times the acceleration times the displacement. Sorry about that. I had to remember which problem we were just doing. So have those written down. Now, again, you won't remember those right now, but I'm going to bring them up. So here's what you would do. You would look at those, and again, we could solve it the way I just did, and you say, what equation do I have? And you'll look at your list of equations, and you're going to see as one of them, v final squared equals v initial squared plus 2a delta x. Now look, we have v final right there. We have v initial right there. We have delta x right there, and we're looking for a. So what you can do is plug in and say v final, which is 8. I'll leave off the units just to save time. 8 squared equals 36 squared plus 2 times your a, I didn't need the parentheses, times your delta x, 88. And just go ahead and solve that. I won't do that here, but you'll get the same answer of negative. You'll have to be careful because of paying attention to signs, because this side's going to end up being negative when I move the 36 squared over there, but you'll get negative 7 meters per second squared. So again, you could do it the old way, 2 steps, which I like. I like you to have to be able to think about multiple steps. But for the final, just find that equation that works. And so that's why it's always good to write down your data, and you just scan all your equations and see which one works. Okay. So I didn't do that on the answer key, actually. So if you're watching the video, that might help. Okay, let's keep going. 14, ball X is dropped while ball Y is thrown up at 30 meters per second. Assuming neither has hit the ground, which will have the greater acceleration 2 seconds later. Again, I didn't say this, I should have, that it's assume no air resistance, because who knows the masses of these, and then the speed's going to affect it or whatever. So anyways, the key here, assuming that I'm talking about no air resistance, is they have the same acceleration. They're in free fall. Again, my bad for not saying they're in free fall or that there's no air resistance, but assuming that's what I meant, everything in free fall, remember that means, actually stop for a second, free fall means something that's moving under the influence of gravity only. There's no friction, there's no air resistance, there's no hand touching it, there's no magnets exerting a force on it. It's only the force of gravity acting on it. So we learned that in free fall, everything has the same acceleration, what we call the acceleration due to gravity, little g. And on Earth, that value is, rounding off, 10 meters per second squared down towards the Earth. So back to the problem, whether I drop a ball from 0 velocity or I throw a ball up at 30 meters per second, when they leave my hand, assuming they're in free fall, they're going to experience the same acceleration. They're going to change by 10 meters per second. So neither, I guess is the way you'll answer it grammatically, will have a higher acceleration. They're going to have the same. Which will be going faster 2 seconds later? Well, let's practice just a skill in our head since it's a convenient number. So remember that the acceleration due to gravity is 10 meters per second squared down. And what that means are things are going to, in free fall, are going to change their velocity by 10 meters per second every second. But it's going to be changing in a downward direction, if you know what I mean. So ball X is dropped straight down. Oops, get rid of that. Ball X is dropped straight down. And so it's going to be picking up speed. It starts at 0, right? So if ball X is starting at 0, 2 seconds later, how fast it's going to be going? Well, after 1 second, it's going 10 meters per second down. And after 2 seconds, it's going 20 meters per second down. But let's look at ball Y. Ball Y is going upwards, so ball X is going down. Ball Y is going upwards. Now, it's going to be losing velocity because it's accelerating at 10 meters per second down. So after 1 second, it's going 20 meters per second up. And after 2 seconds, it's going 10 meters per second up. So long story short, ball X is going to be going 20 meters per second down. Ball Y is going to be going 10 meters per second up. So ball X will be going faster. Okay, we'll actually soon right here get to some calculation questions. 15. On a planet where the acceleration due to gravity is 5 meters per second squared, you throw a ball up at 24 meters per second. How long will it take to reach its highest point, its apex, before it starts coming down? Now we can kind of do this, well, actually we'll do it in our head a little bit later. Let's rely on our equations. Now one thing that will help you is we use a special symbol G for the acceleration due to gravity, but that is acceleration. So that is like our A there. So when we're looking for an equation, we're looking for A. And this is the initial 24 meters per second up, right? And we're looking for time. Oops, question mark, we're looking for time. Now, we're missing some information, and here's what's implied. How long will it take to reach its highest point? At its highest point, what is its final velocity? This is kind of important. The final velocity is 0, right? So keep that in mind. So we know V initial, V final, A, and we're looking for T. So what you can do is find an equation that relates those. Hey, maybe this will be good here or that one. Okay, so we'll do it with the original one, delta V equals AT. Now A, remember, is just the acceleration due to gravity. So the time is just going to be the change in velocity over the acceleration. Well, what's your change in velocity? It was going 24 up and it ended 0. So I'm not going to worry about the sign. So I'm just going to call it 24 meters per second. Technically, we'd say that if we're saying the velocity is 24 meters per second up initially, that the change is negative 24. But then we would define our acceleration as negative also. So don't worry about that. So the change is 24, but we're looking for time. The acceleration is 5 meters per second squared. So you just do 24 divided by 5, which is 4.8 meters. Sorry about the messiness. Meters per second squared. Okay. Oh, I'm sorry. Wrong unit. Again, I'm not going to redo this. It looked weird there when I said that. We were given the acceleration. We're looking for the time. So yes, the meters per second cancels the meters and 1 of the seconds. We're left with 1 over seconds in the denominator. Flips over. We get seconds. Now, going back to what I was about to do, let's do it kind of logically. They're not convenient numbers. The velocity is going to change by 5 meters per second every second. If it's starting at 24 meters per second and we're looking for it to reach its highest point when the velocity is 0, how many seconds will it take? Well, after 4 seconds, it'll change by 20, right? We'll lose 20 meters per second, but we'll still have 4 meters per second left over. So if it's changing at 5 meters per second, and we need to change it by 4 more meters per second, it's going to take another 0.8 seconds. I know that's kind of confusing, but that's the idea there. Maybe doing it before we do number 16, just kind of an easier one, just to kind of do in your head. Let's say we're back, or let's say on another planet. Another planet, the acceleration is 8 meters per second squared. And we throw it up at 80 meters per second. How long will it take to reach the highest point? Well, the way you think about it is, without using an equation, you can, just like we just did, you just do the change in velocity over the acceleration, is it needs to lose 80 meters per second, right? But it loses 8 meters per second every second. So how many seconds will it take? 10 seconds. But yeah, literally what you're doing is you're taking the change in velocity that you need to lose all that velocity, and you're dividing by the acceleration or the acceleration due to gravity. So those might be like nice, quick little questions asking about how long it takes for something to happen. Okay, back to 16. Some of these might be a little quicker, so I'm gonna go ahead and try to just finish this in one video. A ball is thrown up at 20 meters per second on a planet where the acceleration is 4 meters per second squared. Where will it be relative to you 8 seconds later? Assume that's in free fall. In other words, there's no air resistance. Yes, you don't need to use DESPA. It's multiple choice. So let's write down what we're given. We have an initial velocity. Oops, change that pin. An initial velocity. And what I'm going to do is I'm going to call up positive. I don't want to have to deal with ups and down. Up is positive. So if I'm throwing it up and I'm calling up positive, then the initial velocity is positive 20 meters per second. Now here's where it gets a little tricky. What is the acceleration, the next thing I'm given? Because G, it just represents A, the acceleration. Well, acceleration is always down. Acceleration due to gravity, I should say, is always down towards the center of the planet. So if I'm calling up as positive, we've got to be careful here. It will change your answer. The acceleration is negative 4 meters per second squared. Again, I could have said down is positive, so therefore the acceleration would be positive 4 meters per second squared, but then I'd have to say the initial velocity is negative 20 meters per second because it's going up. Now it says, where will it be? That sounds like we want to know its place or its displacement. So we're looking for delta x. Now its time is 8 seconds. Okay, so now we look at that and we think, ooh, that's kind of a tricky one. How are we going to get this? Let's do it the old-fashioned way first, where we didn't know the other equations, and then we'll try to find an equation that will work. So here's, again, the technique that frequently works. I'm trying to find delta x, and I know I can't get that because I need to know the average velocity and the time, right? Remember, delta x, I wrote that here somewhere, equals v average t. I guess I erased it. So I don't have enough information. But look, I have acceleration and time. What can I always find from acceleration and time? Delta v equals at. And I'm telling you, that's how you solve problems. You say, I'm not sure what I'm doing, but I know I can solve for delta v. Maybe I'll stumble upon the answer. So I'm going to take my negative 4 meters per second squared, multiply by 8 seconds, and this is why the negative is going to be important. The change in velocity is negative 32 meters per second, negative. All right. Now, what do I do with this? Well, let's go back to the given information. I know an initial velocity, and I know how much it's changing by, right? So I can find from that the final. The final is always what you start, plus, not minus, how much it changes by. So I'm starting at positive 20 meters per second, but it's changing by negative 32 meters per second. So the final velocity is negative 12 meters per second. I know this is pretty challenging right now because you haven't done this forever, but hang in there. So we're very close now. Remember that we're looking for delta x, and delta x equals v average t. Well, we have the t. We're looking for delta x. Now we just need the v average. So the v average, kind of doing it a different way here, is just 1/2 times the v initial plus v final. So that's 1/2, 20, I'll just leave out the unit this time, plus negative 12. That's the, that's the final, negative 12. So that in parentheses is positive 8, but you divide by 2, so that means the average velocity is 4 meters per second. Now we can solve it. The average velocity is 4 meters per second. The time is still 8 seconds, so it's going to be 32 meters. So there's your answer. Since we called up as positive, that means the ball, or whatever we threw, is going to be 32 meters above where it left our hand. Okay, so again, let's look at the big picture again before I show you maybe a quicker way to solve this using a different equation. Write down your data and look for an equation. And again, just like number 13, the way we did this back in Unit 2 is we had to use 2 equations. But don't give up. Just say, oh, look, I have an A and a T. Let me solve for delta V. And you say, oh, wait, I have delta V and I have initial. I can find and then you start kind of getting closer to your answer. So a lot of you, I'm sure, did it that way. You just kind of stumbled upon it and sooner or later you found the answer. But let's do, now that you can use different equations, let me get rid of this. I think I'll delete it. There we go. Is you'll have written down a bunch of other equations. And among the equations that you'll have is, again, look at V initial We have v initial, we need delta x, we have a and the t. That's the one that I was going to mention earlier. Delta x equals v initial t plus 1/2 at squared. So that's the third equation we used. So let's use that equation because look, I have the initial, I have t, I have a, I have t, and I'm looking for x, or delta x. So I'll just do it really quickly. So you put in 20 meters per second. The time is 8 seconds, plus 1/2. Acceleration is negative 4 meters per second squared. I'll still get the wrong answer. And it's 8 seconds squared. So this gives me 160 meters. This is going to give me 1/2 times negative 2 is, negative 4 is negative 2 meters per second squared. And 8 seconds squared is 64 seconds squared. So this is going to give me 160 meters plus, that's negative 128 meters. And so that gives you 32 meters, which is what we got. So yes, now that you have all the equations, you could just use that equation for that problem. You just look at what's written and you say, okay, what equation can I use? And pretty much, now that we know all 4 equations, I think pretty much any question I give you, you can do it in one step with one equation. Again, that's not on the written answer key, but for those who watch it, you get the bonus. All right, let's move a little faster. I keep saying that. An airplane is climbing an altitude at a constant velocity. What is the net force on the airplane? So I kept doing this back when we learned this. We learned something, that if the net force on an object equals 0, then velocity is constant. And the converse is true. If velocity is constant, what does that say about the net force on the object? Net force equals 0. Okay. It doesn't matter that it's climbing an altitude. You don't need a net force upwards. If it's climbing at constant velocity, we know immediately that the net force on the airplane is 0. Don't get fooled by that one. 18. You are in a car moving in a straight line at 60 miles per hour. The driver steps on the gas and your head slams into the headrest behind you. What caused your head to lurch backwards and hit the headrest? Nada. Oh, let's try to do like a Spanish double exclamation point. Or nothing. What was happening was the car suddenly went forward. You were going along at a constant velocity and the car suddenly accelerated and the car ran into your head. Nothing threw your head back. It was the car lurching forward that ran into your head. So that's kind of my classic question. I know it's all semantics, but nothing caused your head to get thrown backwards. It was just the car going forward. Okay, here's some more easy ones, hopefully. The property that determines how easy or hard it is for an object to accelerate, change velocity, when a force is applied to it is known as its mass or inertia. Inertia is just a description of mass, or vice versa, mass is a description of its inertia. How hard the earth pulls down on an object is known as the object's weight, which we'll symbolize with F sub g, the force due to gravity. All right? Maybe I'll do a little bit of, we'll see if this question reviews it, and if not, I'll do a little review. On the moon versus the earth, your what is smaller? Your weight is smaller. You weigh less on the moon. But your mass stays the same. Okay, I'll go back and review this, but let's just get the answers. Lifting a 1 kilogram rock will be what? Lifting it will be easier because it weighs less on the moon. While shaking the rock will be the same. Now here's the idea again. I kind of use this phrase that, you don't own your weight. The weight is something that happens to you. Your weight is how hard the planet or the moon or whatever is pulling on you. And that changes depending on what planet or moon you're on. So if I'm on the Earth being pretty massive, it's pulling on me pretty hard. So my weight is pretty big on the Earth. But on the moon, smaller mass, it's going to pull on me less hard. So I weigh less on the moon. So your weight changes depending on where you're located. But your mass is something you own. That is your inertia. It doesn't change no matter where you are. So your mass is the same on Earth as if you were in the middle of outer space and quote unquote weightless. Yeah, you would be weightless, but you're not massless. You always have the same inertia. So getting back to that second part of the question, lifting something on a planet or a moon, you're battling the planet. You're lifting the weight. And so since the objects weigh differently on the moon and the Earth, it's harder to lift the object on the Earth than on the moon. But shaking something involves accelerating it. You're speeding it up, slowing down, turning it. And that is dependent on the inertia of the object or the mass of the object. Remember, I had those videos of me in that little spacesuit and that helmet, and I was lifting things on the moon or shaking them. Maybe that will be stuck in your mind there. Okay, mass uses the SI unit kilograms, not grams. It's kind of a weird one. They decided to use kg as the base SI unit for that. And the imperial unit is the pound, lb. Force, I'm sorry, I made a mistake because I was thinking whether I was going to write pound or lb, but that neither was correct, right? The imperial unit of mass is that weird one, slug, my bad. Force or weight uses the SI unit of Newton. Oops. I don't know why I did that weird line. The Newton, and the imperial unit of, there you go, pound. Okay. It's all going to come back to you, I hope. Some easier ones. The block is moving to the right at constant velocity. So immediately, what are you thinking? Net force equals 0. If there's one other force acting on it, draw and label its arrow. So it must be 10 pounds to the right? If we're getting, I hope that's about the same length. That means the net force is 0 on it, which means it's constant velocity. Now, I don't know if I asked this later, but if I drew that object there, I'm not sure if this is on the final, probably not, but I'll go ahead and ask it, is if I drew that thing there with the 10 pounds to the right, and I said, true or false, this object is not moving, you would say, well, I guess that depends how I word it. You'd say false, because it could be moving, right? But it would be moving at constant velocity. So having the net force equals 0, the two arrows canceling, doesn't necessitate that it stopped. It just means it's not going to be changing velocity. So if there's 10 pounds each way, it's either stopped and it stays stopped, or if it's moving, it's going to keep moving with the same velocity. I hope that made sense. All right. 21. There are 3 horizontal forces on the block. I've drawn 2 of them. The net force is 5 newtons to the left. You got to make sure which way is the left and right. Draw it on your hands if you don't know. An L and R on your hands. Draw the arrow for the third force. So if the net force is 5 newtons to the left, right now we have 17 to the right? What will it need to be the total to the left? The total, not the answer I'm looking for, to have the net force being 5 newtons to the left. It'll have to be 22, right? So we need 14, and try to make it proportional. Maybe that represents 14. So now that we have the answer there, it should make sense. The net force to the left, not the net force, but the total force to the left is 22 newtons. To the right, it's 17 newtons. So the net force, it looks like it's 5 newtons to the left. 22, a 1 pound ball. By the way, what is that describing? The mass or the weight? The weight, right? Because I'm saying pound. Is tossed straight up at the very top of its path, just before it starts to come back down. So at its apex. What is the velocity? It's 0. It's turning around. So it was going up and slowing down, and it's about to come down and speed up. But at its apex, it is going to be 0. What is the acceleration? It is not 0. And I talked many ways about this. One of them is, let's say it reached the top of its path, its apex, and its acceleration were 0. Could it change velocity if its acceleration is 0? No. So what would it be doing there? Hovering forever. So it is accelerating. Gravity does not turn off just because a ball reaches the top of its path. Gravity is still pulling on it. So the acceleration is still negative, if we want to call it down. We don't have to, but if we're saying down is negative, 10 meters per second squared, or 9.8 if you want to be more exact. What is the net force on it? Well, I assume, good. I was going to say, I didn't say that there's no air resistance, but if it's at the top of its path, then there is no air resistance because it's not moving, for that tiny fraction of a second. So there's no air resistance. We don't have to worry about it. What's the only force on the ball at the top of its path? It's weight. And what is the weight? It is 1 pound. Okay. You're on a train moving at a constant velocity. If you throw a ball straight up, where will it land? Okay, it's kind of you'll remember this one. So if we're in a train and there's no wind blowing through the windows, the ball is moving with you forward at a constant velocity. So when you throw it up, just because it leaves your hand, it's not going to suddenly slow down horizontally. It's going to keep moving at whatever velocity it had because it has that inertia. So it's going to land straight back in your hand. But let's say, part B here, if you threw it up, but the train suddenly speeds up, where will it land? Well, the ball's not going to pick up speed like you are because it's not attached to your hand or to the chair or whatever. So it's going to land behind you somewhere. 24. Some more graphs. You throw a ball up, draw the position, velocity, and acceleration graphs from it leaves your hand until it comes back down, but it hasn't hit your hand yet. So assume up is positive. That's the U. So think about what's going to happen. It's going to move up, slow down. At the top, it's going to be temporarily, velocity is 0, and then it's going to come down and be speeding up. So without me quite explaining it beforehand, this is, maybe it's not, we'll call 0 your hand, it doesn't matter. So you're going to get something that looks like this. So what does that say? It's moving up, but because it's curving, it's slowing down. It's going from steeper to less steep. Right there, the slope is 0, which means the velocity is 0. But now it's heading in the downward direction and becoming steeper, which means it's speeding up. Now on a velocity curve, it's heading up at first, right? But slowing down. But this is the tricky part. We're assuming it's a constant acceleration, so I guess I would need to say it's no air resistance. So that represents something moving upwards and slowing down. Remember a velocity graph, when you reach the x-axis, it's stopped, even if it's just temporary. But now, once it's reached its apex, it's going to be heading downwards. So we need to have a downward velocity, but speeding up. And again, we'll assume it's a constant velocity. Or I should say, not constant velocity, a constant acceleration. So something like that. So again, convince yourself that that's a ball being thrown up, then coming back down. It's moving up, slowing down, and turns around. Remember, velocity graph, when it crosses the x-axis, it's turning around, and then heads down and picking up speed. Now, again, assuming that we have a constant acceleration, remember the slope of a velocity graph is the acceleration, and the slope there of a velocity graph is constant. So what is the acceleration? It's constant, but is it up or down, or is it positive or negative? Well, the slope is negative, right? Or down, because we're heading in the down direction. So the acceleration is down, but it's a constant acceleration. So it would look like that. And in fact, if we're on Earth and there's no air resistance, this value right here, what is the acceleration? Negative 9.8 meters per second squared. Okay, sorry if that's a little fast, but I don't know if I'd ask them. Maybe I would, but it would just be multiple choice. Below it, this looks familiar. I just drew this. Here's an acceleration graph. So it's going to be the backwards of this one. Sorry for the repetitiveness. Draw the rest of these. A velocity graph starting from right here with this velocity. Well, this says it's a negative constant velocity. Don't worry about the fact that it's constant. Let's just focus on, I said velocity, negative constant acceleration. Let's just focus on the fact that it's a negative acceleration. So negative acceleration doesn't mean you're slowing down necessarily. The negative sign for acceleration just means your change in velocity is negative. Okay, that still is confusing. But here's what I kind of taught you to learn about is if your current velocity, not the change, and your acceleration have the same sign, like they're both positive or they're both negative, that means you speed up. Sorry about my notation there, that doesn't quite make sense. But if your current velocity and your acceleration are both positive or both negative or both north or both south, that means you speed up. But if your velocity has the opposite sign of your acceleration, that means you slow down. So that's the significance of the sign of acceleration. If the sign or direction of your acceleration matches your current velocity, that means you're going to speed up. If it doesn't match it, if it's the opposite sign, opposite direction, it means you slow down. So let's go to the graph here of velocity. What is the sign of my velocity? It's positive, right? But the acceleration is negative. Does that mean I'm going to speed up or slow down? You're going to slow down, right? And so we'll assume it's going to look like this because, again, that's a constant acceleration, which means I'm going to have a constant slope. I know that's kind of difficult, but maybe you get what I'm talking about there. So let's say that is the, I don't say where to start, I guess, where to stop, so I'll just stop there. So now let's do a position graph starting from that point. What does this show? Something with a positive velocity that is steadily slowing down, right? So here's our thing here. We need a positive velocity, so which way do I need to go? Well, positive velocity means it is heading in the positive direction, but I need it to slow down, so it'll look something like this, right? And oops, I didn't mean for it to snap like that. So it's something like, it slows down like that, okay? And I actually stopped at 0, so I'll stop at the horizontal. Now, if I kept going, I don't think I said that, like I went all the way here, it's kind of like this figure over there, where I would redraw that one. Oops. Again, if I continued there, I would need to show something that is, for this part, positive velocity slowing down, then negative velocity speeding up. So I'd say positive velocity slowing down, now negative velocity speeding up. Okay. Here's a quick one. I don't know if I'll ask this one, but we'll do it. A dog is on a skateboard when he flies off a cliff. As shown, he lands the distance shown from the edge of the cliff. We're doing this for some lab about, understanding how horizontal velocity does not depend on the vertical velocity and vice versa. So the fact that he's falling is not going to affect how far he moves horizontally. So it turns out to be kind of an easy problem. There was a lesson to be learned in this kind of easy problem, but let's just solve it. So we want to know how long, so we're looking for t, right? Would it take for him to hit the ground, knowing his velocity, which we're assuming is not changing, and we know his change in position. And that's kind of the key here, is we're going to be talking about his horizontal motion. His horizontal velocity is 3.5 meters per second. So just because he's falling downwards, is that changing his horizontal velocity? Nope. As long as there's no horizontal forces acting on him, he's not going to change his velocity. So he's going to stay at 3.5 meters per second horizontally for that entire time. Sure, he's picking up speed vertically, but that doesn't affect how far he moves horizontally. So this just comes down to using that old chestnut, delta x equals v average t. So t equals his displacement over his average velocity. So his displacement was 17.5 meters. And we're assuming that now this was a mistake. Let me go over this. And again, bonus for those who are listening to this is, by the way, just get the answer there. That's going to end up being 5 seconds. His velocity is 3.5 meters per second the whole time. So his average velocity is 3.5 meters per second. Here's what quite a few people do. They say, okay, it's 3.5 meters per second. I want the average. Well, I guess he started at 0, and then he ends up at and they get 1.75 meters per second as his average velocity. No, he started at 3.5 meters per second. He ended at 3.5 meters per second. His average is 3.5 meters per second. So don't say he's starting at 0 and have his average velocity half his actual velocity. Okay, a few more. So a couple of ones where I'm going to say probably, well, no, I don't. Oh, this is a quick one. We have one more kind of DESPA one over there. So we're getting close to the end. Hopefully this is close to an hour, not much more. You toss a ball A up at 30 meters per second, throw ball B down at 20 meters per second, and drop C with no efficient. Oh, this is confusing, right? Let's draw a figure. So we toss A up at 30 meters per second. We throw ball B down at 20 meters per second. I'll just write 20. And then we drop C, lots of them. We just drop it. And D, we're throwing horizontally at 15 meters per second. Ooh, I don't know where this question's leading. It's kind of a weird one. I don't remember this one. After you let go of each, which has the greatest vertical acceleration? Again, my bad. Yikes. Well, I could get away with this. I should be saying no air resistance, i.e. free fall, right? You know better than I do. But I guess what I'm saying is right when you let go or right when you drop them before they have a chance of starting to move. So just as I let go of these, if they're not quite moving yet, they haven't experienced air resistance, even though I should have still said no air resistance. So anyways, that's like the question before. After I just let go of each, if they're all in free fall, they have the same acceleration, the acceleration due to gravity. Vertically, they're going to change by 9.8 meters per second. If they had different masses, would that affect your answer? No. Mass, remember, gravity has the same acceleration on everything, no matter what their mass is. If you draw, with no air resistance, a bowling ball and a tennis ball, if there's no air resistance, they have the same acceleration. It doesn't matter what their mass is. Okay, here's one. Here's a velocity graph. Draw the position graph for this. So again, let's interpret this, but we're actually going to need to do it numerically. This is constant velocity of -6 meters per second, right? So I can say the V average is -6 meters per second. Now again, the average velocity is not -3. Did it ever start at 0 meters per second? No, it started at -6 and it ended at -6. So the average velocity is -6. And what's the time? 10 seconds. So I need to draw a position graph starting at this position. So I want to know what the change in position will be. So delta x, the change in position, is the average velocity times the time. So that's just -6 meters per second times 10 seconds. It's going to change by -60 meters, -60 meters. So if I'm starting at -30 and I'm going to end up changing by -60 after 10 seconds, at 10 seconds, I'll be at -90, right? Now notice it's a constant velocity, so therefore that should be a constant slope on my position graph. I'm probably going to miss this, but I'll try to hit it there. There we go. So that will be the figure. All right, finally, let's do this one and get out of here. Let's do another one where, again, it's not really we're going to do DESPA. I'm just getting rid of that to get some space. But let's just, again, identify some things, but also to waste a little time, I'll rewrite the information. But first part is always to identify each of these. So I just told you, actually, they're kind of written in there, so I'll go ahead and just start by writing it. The initial velocity is positive 10 meters per second. I'll just leave off the positive. The A is positive 5 meters per second squared. I'm going to also do this one probably two ways, I think. That's what's going to end up being. And the V final is equal to 35 meters per second. And what am I looking for? How far? So it's always means in physics, delta x. So let's do it the long way, and then again, we'll look for an equation that we can use to solve this. So again, let's say we're stuck here and we're looking for delta x. One way you can do this is saying, well, if I'm looking for delta x, one way to find it, just using our original two equations that we had for this unit, is this, right? Do I have the V average? No, but again, key piece of information. Whenever you have initial and final velocity, what two things can you solve for? The delta V and, how do I put equal, and the V average. So in effect, I do have the V average. So I have the V average, I'm looking for delta x. So to solve this problem, what's the only thing I need to solve for? T. So then you go, I'm stuck. How do I get T? Go back and look at your equations and you say, oh, wait a minute. There's one that says delta V equals AT. So if I'm looking for T, and I have A, I can solve for it, T, if I can find delta V somehow. Oh, and that's right. Whenever I'm given initial and final velocity, I can solve for delta V. So again, that's what you can do. Now, the other way you can solve it, again, is not by looking, in the future of what you need to find. Again, let's say you're just lost and you go, I have acceleration and I got V final and V initial, which means I could solve for delta V. What can I find with delta V and A? Oh, that's right. I can use this. So let's go ahead and solve this. So I have, in effect, delta V, because I have the initial and final velocity. I have A, and I want to solve for T. So just doing it in our head here, what is the change in velocity? We went from 10 to 35. It's 25 meters per second. And the acceleration, I just purposely made really convenient units here, is that. So the time is going to be 5 seconds. And now you say, oh, great. I have time now. I can get the average velocity from the given information, so I finally can solve for the delta x. So delta x equals v average. So the average, what's the average between 10 and 35? You add them, 45, and divide by 2. So the average is 22.5 meters per second. And the time, again, I'm using this equation here, is 5 seconds. And that is going to be is that 112.5? I think so, yeah. I don't know what I just said, but I'm just kind of talking so fast now, I don't even know what I'm saying. So there we go, a 2-step problem. I'm not going to put a lot of these on the final. There's so many. I can only ask 100 questions for the entire year, only 50 on physics, so I can't do a bunch of these. But I will try to do one where you might need to use 2 steps. But I told you that you're going to be able to use all the equations, and if you do, you could find an equation that you can do it in 1 step. So let's look back at the equations I wrote here. So those equations there, I know it's better if you have them side by side, but let's see what we can use. We're looking for delta x, and we have blah, blah, blah. So if you look at that, here's one that has delta x. Oops, right there, get my pen. And so do we have the initial time and acceleration? No, okay, we can't use that one. But what about this one? V final, V initial, A, and delta x. V final, V initial, A. There it is. So let's use that one. V final squared, and we'll do it in 1 step, equals V initial squared plus 2A delta x. So we got the V final. Excuse me, I'm just going to not put the units. V initial. Acceleration is 5. Again, my bad for not putting units, and we're looking for delta x. So 35 squared. Okay, I got my calculator here. I just want to solve it for you. 35 times 35 equals 1225. I bet some of you knew that. Equals 100 plus 10 delta x, right? So we're going to subtract 100 from both sides. This is 1125 divided by 10 equals delta x. So what's 1125 divided by 10? Well, it should look familiar, 112.5. And I'm going to trust that I did it right. And so, of course, if I'm using SI units everywhere, I'm going to get the SI unit for delta x. Okay? So thanks for listening. I hope that helped you. I know it's very intimidating to go back and learn these things, but I believe in you. Okay, take care.